Hey guys, so last section of Unit 4, and we're going to talk about Earth's geography and how that relates to climate. And we're going to talk about El Nino, La Nina, and the Southern Oscillation. So let's go ahead and jump into our PowerPoint here. And eventually this will work for me. Maybe. All right, just here. All right, so let's talk about Earth's geography and climate. So all of this is related to what we've been talking about with the seasons, with those global wind currents, and all of those pieces come together when we talk about geography and climate. So this is our planet. Here in the red zone near the equator, we have tropical climates. So this is those areas that receive huge amounts of solar radiation. They're very moist. And as the warm air rises, the moisture condenses, it falls back down. We have lots of rain and we have lots of heat. So that's what we consider the tropical climates, and those are centered around the equator. Then between the equator and those desert regions, so between the equator and that 30 degrees north and 30 degrees south, we get into what we call subtropical zones. So again, lots of heat from that intense solar radiation, but not quite as wet, because we don't have that adiabatic cooling and resultant precipitation. Above these subtropical zones, above and below the subtropical zones, we have what we consider the temperate zones. And this is most of the United States and Europe, the southern part of Russia, as well as the southernmost tip of South America. And so these are the temperate zones. Below that, we have what we call, and above that, we have subpolar. So this is near that 60 degrees north and south latitude. So here is where we find our taiga forests. And then above and below that, we have our polar climates. So there's where we have our tundra, very, very cold and very, very dry. So what determines these climate patterns? Well, there's a lot of pieces that come together to make these climate patterns. The number one piece is that solar energy, okay? So that angle of the sun's rays is going to determine whether it comes through as an intense level of solar radiation or a lesser level of solar radiation. But in general, all of our climate patterns are driven by solar energy, because the global air circulation as well as ocean currents are driven by the solar energy. So as we talked about with seasons, when it's striking at a low angle, that means that there's going to be a more direct angle is going to give us more solar radiation. The lower the angle, the less of the energy that is able to penetrate through, because it's having to go through more of the atmosphere here at this low angle than it does at this more direct angle. So what this means is that heat and precipitation are not distributed evenly around the globe. So heat and precipitation very heavy at the equator. We know that 30 degrees north and 30 degrees south, it tends to be very dry, though still relatively warm. And up here at these polar extremes, even when they are receiving a large number of hours of sunlight, as they do in their summer seasons, it is not a strong radiation because it has to pass through so much of the Earth's atmosphere before reaching the surface. So again, that global air circulation, Coriolis effect, the polar, Farrell, and Hadley cells, those ocean currents, and then the angle of the sun's rays. The other thing that really influences climate is these topographic features. Number one, especially when we look at this comparison over here on the right, is proximity to water. So if we think about it, Wichita has big extremes here. In January, its low is 20 degrees Fahrenheit. Its high in July is 92 degrees Fahrenheit. Over here, the data is from Virginia Beach, obviously very close to us. Our low in January is only down around 30 or 31 degrees, and our high is only up to 89. So big differences. Wichita gets a lot colder and a little bit hotter. And then we look at San Francisco, California, and their low in the winter is warmer still, only 46, but their high only gets up to 71. So what's the deal? Because these are all at very similar latitudes. So why do they have such different temperatures? And the answer to that question is really about their proximity to oceans and to the particular currents that they're near. So Wichita, Kansas, obviously not near any oceans. Anytime we're near a large body of water, that provides an insulating effect. And so you get less extremes. Your lows don't get as low and your highs don't get as high. But then when we think about the way that our global currents work, we talked in class about the fact that here on the east coast of the United States, we have this warm Gulf Stream current coming up the east coast from the tropics. Whereas here in San Francisco, California, we have a cold polar stream coming down from the north or from the northern reaches of the Pacific Ocean. And so their prevailing water temperature is much colder than our prevailing water temperature. And that explains why our highs are higher than in San Francisco. Their current flows closer to the shore, which is why their low doesn't get as low. Our current tends to stay a little bit farther off the coast of Virginia. And then the other piece that really influences, the other topographic piece that really influences climate is mountain ranges. So if we think about, we're going to go back to California here, the west coast of the United States gets a fair amount of rain, but you hear all the time about wildfires in California. And the reason you hear about wildfires in California is that there's a mountain range that runs down through the state of California. The prevailing winds in California come from the west, and as they rise up and over these mountains, we get this adiabatic cooling again because it's going up through into those areas of low pressure. And so it's expanding and cooling, and it's dropping all of its rain on what we call the windward side of the mountain, which in California is the westward side of the mountain. As it goes over the mountain and falls, it's now very dry air. And so the eastern side, in this case, the leeward side of the mountains is very dry. And this effect is called a rain shadow. So a rain shadow basically means that all the rain gets dropped on one side, and therefore there's no moisture left when it reaches the other side. There is rain shadow effect in lots of places. It's not just on the Pacific coast. It's not quite as pronounced on the East Coast, but it does exist in some areas. Okay, so that's how geography and climate are related. Let's go ahead and talk about El Nino and La Nina. And you may have heard about El Nino, less likely that you've heard about La Nina, but they do get talked about on the local news as part of our weather cycles. So they can get a little bit overblown, as we see in this comic strip, and cause panic. Let's talk about what it is, what they are, so that we can understand what we should be concerned about and how it impacts the environment. So before we can talk about El Nino and La Nina, we need to talk about this idea of a gyre. So a gyre is a large-scale water circulation. So this is those global currents that we've talked about. So they tend to be circular patterns. In the northern hemisphere, they move clockwise. In the southern hemisphere, they move counterclockwise. And this again comes down to the Coriolis effect and the driving winds, the prevailing winds that drive them in this direction. As these gyres come up from the South Pole or down from the North Pole, They bring colder water as they go away from the equator, that's up in the north and down in the south. They bring warmer water. So these are driven by solar radiation. The warming of the water here near the equator is going to push that warm water away from the equator because it's expanding and so it's moving. And this is driven by solar radiation. And then the cycling is driven by the Coriolis effect. Okay, so with those gyres in mind, let's talk about the idea of an upwelling. So in an upwelling, our surface winds, they might be moving perpendicular to the shore, or they might be moving parallel to the shore. But either way, they're pushing surface water away from a particular area. And when that water is pushed away from an area, this deeper, colder, more nutrient-rich water is going to get pushed up to the surface to replace the water that's being lost. The deeper water is more nutrient-rich because of that idea of marine snow. All the life that lives up here near the surface of the water, phytoplankton and all the things that dine on phytoplankton, as they die and decompose, that falls down through the ocean into this deeper water. So as this colder, nutrient-rich water comes up, it brings lots of nutrients for the phytoplankton, which causes more phytoplankton, which then supports larger food webs. So this map, courtesy of NOAA, the National Oceanic and Atmospheric Administration, shows you all of these areas of upwellings. So you'll notice that there's large areas of upwellings at the edges of most of our continents. So this nutrient-rich water is coming to the surface, encouraging that growth of phytoplankton, and it's supporting these large marine food webs. So you can have this with a wind that is parallel to the shore, or you can have it out in the open ocean, and we'll talk about those as well. So along the edges of continents, winds blowing along the coast push that surface water away from the land and draw the water up from below. Okay, so this is just a different image of that. You can see that even though the wind is not blowing away, it's blowing south, and that's causing the warm water to be pulled away from the shore and the cold water to be pulled up to the surface. In the open ocean, this is more often caused by the trade winds. So especially near the equator where the northern trade winds and the southern trade winds come together, they're going to push that warm surface water away from the equator, which is going to bring that cool water up from below. So these are the normal patterns. What happens during El Nino? Every few years in the southern Pacific Ocean, please notice that it is the southern Pacific Ocean, the prevailing tropical trade winds are either going to weaken or even potentially reverse their direction. That means that those warmer waters from the Western Pacific are going to move towards South America. And we're not going to see those upwellings of cold, nutrient-rich water. So what's that going to look like? Normally, we have this upwelling here off the coast of South America, and the warm water gets driven to the west towards Australia and New Guinea and New Zealand. In an El Nino year, because those trade winds get flipped, that upwelling does not happen. Instead, we have warm water off the coast of South America, and we're going to get a warmer winter in North America. Even though these reversals occur in the South Pacific, they affect weather worldwide. So what are some of these potential effects? Because those upwellings don't happen off the South American coast and to a certain extent off the Central American coast, we're going to have a major decrease in nutrients. If we have that decrease in nutrients, we're going to have a reduction in primary producers. We have a reduction in primary producers. We have a cascading effect on the entire food chain, the entire food web. It can cause a decline in fish populations. It can cause changes in the migratory patterns of birds who depend on those fish populations, along with migratory patterns of mammals that depend on those fish populations. It can also alter the weather of 2/3 of the globe, especially along the Pacific and Indian Oceans. So you can see that it's wet and warm all the way across the southern Pacific. It's dry and hot over here in Australia, New Zealand, Southeast Asia. It tends to be warmer as well in Japan and the other Pacific Asian countries. Warmer than normal in North America, here in the Pacific Northwest, in the northern US and Canada. It also results in drought in Australia and New Zealand, as well as parts of Eastern Africa. Although there are other parts of Eastern Africa closer to the equator that actually have unusually high rainfall. So the same weather condition causes different problems in different areas. It frequently results in heavy rains and flooding in the southern United States. So these are our normal conditions. Our warm waters get pushed westward. We get surface winds blowing westward, and we have our normal cycling and our upwelling. In an El Nino year, because the normal trade winds are running into these reversed trade winds, the rain tends to fall out in the ocean, which is going to cause drought in Australia and Southeast Asia. But it does create storms for the American Pacific Northwest. Okay, kind of the opposite of an El Nino is a La Nina. So a La Nina cools those coastal surface waters. These prevailing trade winds are stronger than normal. So that brings a whole cooling effect to the Pacific coast of South America and Central America. It brings back those upwellings. La Nina actually can cause more Atlantic hurricanes. It causes colder, wetter winters in Canada and the northeastern United States, but it causes warmer, drier winters in the southeastern and southwestern United States, which tends to lead to more wildfires. It also leads to wetter winters in the Pacific Northwest. If you're a skier, this is a good thing. Lots of the American ski resorts get great winters in La Nina years. This can lead to torrential rains in Southeast Asia, those monsoon seasons that cause flooding and landslides, and it can affect crop yields in all of South America. Okay, that's it for El Nino, La Nina, and what is known as the Southern Oscillation. As always, if you have any questions, let me know.